Urban coastal cities are facing increasing pressure from climate change. Rising sea levels, erratic rainfall, and rapid urban expansion have made water supply systems more fragile and energy-intensive. In Thailand, cities like Pattaya exemplify this challenge. Long pumping distances, steep topographies, and aging infrastructure lead to high electricity use and carbon emissions. This study aims to respond to these issues by integrating water, energy, and carbon management into a single framework, allowing urban utilities to operate more sustainably while maintaining reliable service delivery. The study set out to develop and test an integrated water, energy, carbon optimization framework for coastal urban water systems. Its objectives were threefold. First, to identify inefficiencies in hydraulic and energy performance. Second, to quantify how these inefficiencies contribute to carbon emissions. And third, to propose practical optimization and policy strategies that align water utility operations with Thailand's national decarbonization goals and the United Nations Sustainable Development Goals, particularly SDG 6 and SDG 13. The research combined EPANET hydraulic modeling, SCADA-based monitoring, and GIS spatial analysis within a multi-objective optimization framework using the NSGA2 algorithm. The study covered 5 water distribution zones in Pattaya City. Data were drawn from the Provincial Waterworks Authority, including real-time flow, pressure, and pump data at 15 to 30-minute intervals, as well as grid emission factors from the Thailand Greenhouse Gas Management Organization. The modeling process involved calibration with a mean absolute percentage error below 5%, ensuring high accuracy. Sensitivity analysis then evaluated how pipe roughness, pump efficiency, and leakage rates affected energy use and carbon emissions. The system's energy and carbon performance were finally simulated under multiple scenarios to identify the most efficient operational strategies.
The baseline analysis revealed stark contrasts between zones. Energy intensity ranged from 0.42 to 1.32 kilowatt-hours per cubic meter, and the highest losses occurred in older, high-elevation networks. Using the integrated optimization approach, the best-performing scenario, called S5, combined variable frequency drive controls, pressure zone management, and targeted pipe rehabilitation. The results were striking: 32.6% less energy use, 30% lower CO2 emissions, equivalent to roughly 540 tons of CO2 per year, and 97% service pressure compliance. Over 2 decades, this would prevent approximately 10,800 tons of emissions, proving the model's long-term viability. These improvements came with strong economic feasibility, achieving a net present value of about USD 298,600 within a 5-year payback period. The WEC framework offers both technical and policy insights. Utilities can use it to optimize pump scheduling, prioritize rehabilitation projects, and improve monitoring systems. Policymakers can use the findings to design evidence-based tariffs, allocate infrastructure investments, and promote low-carbon incentives. The study suggests 3 policy phases: short-term actions such as pressure adjustments, medium-term measures like pipe rehabilitation and GIS-based leakage detection, and long-term strategies incorporating renewable-powered pumping. Furthermore, the study recommends tariff protection mechanisms, such as lifeline water rates, to safeguard low-income households while supporting financial sustainability.